So in this episode, I'm going to talk about three papers. One will be on methane emissions from Beringia. Another will be on sea level changes in northwestern Canada. And finally, I'll talk about a surface temperature reconstruction of the past 485 million years. So the first paper on methane is titled Methane Flux from Beringian Coastal Wetlands for the Past 20,000 Years. And this is by Fuchs et al. It was published in the November 15th issue of Quaternary Science Reviews. And as a disclaimer, I am the third author on this paper, so this is a bit of self-promotion. So methane, of course, is a very powerful greenhouse gas, and low-lying coastal wetlands, tidal wetlands, are a natural source of methane gases. And in the past 20,000 years, we've seen sea level rise, and the Beringian Shelf is a very flat area, and during the last glacial maximum, most of it was exposed. And so when the sea level rise happened, the amount of coastline was actually greater than it is now. And it was hypothesized that in the past, when the sea level was rising, the amount of methane emissions from the coastal wetlands was probably higher. And so Beringia is the area that includes Alaska and eastern Siberia. And right now there's the Bering Strait, which separates Alaska and Siberia, but 20,000 years ago, when sea level was lower, that area was all land, and gradually, as the ice sheets melted, the sea level rose, and eventually that shelf area got flooded, and that happened between 20 and 5,000 years ago. And so Fuchs et al. Used paleomist, which is a paleotopography data set that I created, and they wanted to check to make sure that the paleotopography reconstruction from paleomist actually reflected the real changes in the coastline area. And so they took sediment cores from the Beringian Shelf, which contain freshwater peat. So the freshwater peat is an indication that sea level was lower than the elevation of that core sample. So basically, Matthias Fuchs, who's the lead author, took this data and plotted against the coastline history from paleomist and validated that more or less this topography reconstruction is consistent with these freshwater peat data, so that the topography did not flood, or the reconstruction did not show that the land was flooded before the peat stopped accumulating. And so because we know that the topography reconstruction more or less represented the sea level change history in that region, he used a model to calculate the amount of methane flux from coastal wetlands if the configuration of the coastline was changing during the deglaciation. So based on that, between 9 and 16,000 years ago, it was estimated that the amount of methane from these coastal wetlands was roughly double what it is now. And the thing is, though, the amount of methane being emitted from the coastal wetlands is not really substantial compared to other things like peatlands from terrestrial areas. But one of the points is that although the amount of methane emitted from these Beringian coastlands are not great, the fact is that this doubling of the relative amount of methane being released actually started earlier than the development of these terrestrial peatlands. So it might have contributed a little bit to the global warming that was happening during the deglacial period. So yeah, it was interesting to be involved with that. I didn't know about methane fluxes, so now I know a little bit about it. So I thank Matthias Fuchs for inviting me to be part of this study. The second paper I'll talk about is actually somewhat related because it's on paleo sea level changes and ice sheet changes in northwestern Canada in this area close to Banks Island and the Amundsen Gulf. So the Amundsen Gulf separates Banks Island from the mainland of North America. And they were interested in the history of what went on in that area for the past 30,000 years. And this paper, which is titled Passage and Removal of the Amundsen Gulf Ice Stream, Northwest Laurentide Ice Sheet, recorded by the Glacial and Sea Level History of Southern Banks Island, Arctic Canada, is by Vaughan et al. And it was also published in the November 15th issue of Quaternary Science Reviews. So yeah, if you Banks Island is in northwestern Canada, and one of the interesting things about the history of investigations of Banks Island is that the people who originally went there thought, oh well, this island has been glaciated, but this glaciation was quite ancient, and so they proposed during the last glacial maximum, so about 20,000 years ago, that Banks Island was actually not covered in ice, even though the rest of Canada was basically covered in ice. And a group of scientists based out of the University of Alberta went back there in the 2000s and completely revised the history of the glacial history of the island, and said, well, the evidence we have is that it was glaciated at the last glacial maximum, and that might have been the only time it was glaciated. So it basically very much flipped the script on the history of this island. And this paper by Vaughan et al. is a geomorphology and geology paper, and it's quite long. It is a review paper after all. And anyway, they focus mostly on southern Banks Island, and one of the interesting things they found was that the retreat of the ice from Banks Island had to have happened before the ice stream that was flowing, the glacier that was flowing through the Amundsen Gulf. So they found evidence that there was a lake on southern Banks Island, which was dammed by the ice in the Amundsen Gulf, and they found shorelines and deposits all throughout there. And the thickness of the ice could be estimated because the highest point in southern Banks Island is about 720 meters high, and they found what are known as erratics. So erratics are rocks that were transported by the glacier from somewhere else, like far away. And based on what these rocks were, they said, well, this is from the Amundsen Gulf ice stream. And because they found these rocks, they're like, well, the Amundsen Gulf is 400 meters deep, and this mountain is 720 meters high, so the thickness of the ice was at least 1,100 meters. They also investigated the sea level changes, and so on the western part of southern Banks Island, they find evidence that the maximum sea level high stand was 11 to 15 meters, but as you go further west, it's up to 41 meters. And what that indicates is that two things: that the deglaciation happened earlier on the west side than the east side, and that the ice thickness was likely less on the west side, and that makes sense because you're further from the center of the ice sheet. One interesting thing is that the high stand deposits in the western part of Banks Island don't have any fossils in them, so that is an indication that the deglaciation happened before the Bering Strait got flooded. So yeah, related to the previous paper, that the shells and the marine shells and marine mollusks could not actually get into the Arctic Ocean until the Bering Strait was flooded. And so the oldest shells they found were 12,900 years ago. So they estimate that their estimates that the flooding of the Bering Strait happened about 14,700 years ago. So the deglaciation of Banks Island happened before that. And another thing that they found was that they find shell fossils in the glacial sediments themselves, and these obviously predate when the ice advanced over Banks Island. And based on the ages that they found on these shells using radiocarbon dating, they estimate that Banks Island was not glaciated until sometime after 24,000 years ago. And that's quite late because the last glacial maximum period started about 27,000 years ago. And they estimate, based on analogs on the mainland across the Gulf, that the maximum extent of the ice might have been as late as 16,000 years ago. So the ice advanced all the way to the edge of the continental shelf off the west coast of Banks Island, and it didn't stay there very long. But based on the thickness of the ice, the icebergs, there are scours on the bottom of the Arctic Ocean at 1,000 meter or even deeper depths, and the thickness of the Amundsen Gulf ice stream was thick enough to produce icebergs that would have been able to touch the ocean floor at that depth. And yeah, it's as somebody who's planning to model the ice sheets in that area, this was a very nice study for my work. The final paper that I will discuss is on a temperature reconstruction of the Phanerozoic, and this is titled "A 485 million year history of Earth's surface temperature" by Judd et al. And it was published in the September 20th issue of Science. So the first thing you probably asked was, what is the Phanerozoic? And the Phanerozoic is defined as the time period when complex life forms started to appear on the Earth. And by complex, they mean things that have preservable parts, like shells. So prior to the Phanerozoic, the animals and other creatures did not secrete carbonate shells or anything like that. And the rise of complex life obviously had a major influence on the Earth. And during the Phanerozoic, the positions of the continents changed a lot. So it's kind of tough to understand the climate changes unless you account for that as well. And so what Judd et al. Did is used a technique called data assimilation. So there are two primary ways that you can infer past climate. You can use proxy records, which I talked about earlier, and also climate modeling. And the proxy records provide you with a more direct way to understand what the past climate was. However, the issue is that they're heterogeneous. Like you do not have proxy records that cover the entire world. Some of that is because we haven't measured everywhere, but also because the geological record is very incomplete. And the climate models give you a complete record of global climatic conditions, but the issue is that climate models require a lot of computational resources, so they're usually run at a very low resolution, like grid cell sizes on the order of hundreds of kilometers in some cases. And also climate models are not complete. Like they're missing physical processes in them because we don't have a complete understanding of the climate system. So what Judd et al. Did is use a technique called data assimilation, and this is basically a way to take the climate model output and statistically correct for these problems in the climate model using the proxy data. So it's basically a machine learning technique where you take the climate model output and adjust the climatic fields using the data and iteratively create sort of an uncertainty range of what the climate was. So the data that they used were proxy records of ocean surface temperature changes, and the reason they used the ocean surface temperature proxies is that terrestrial proxies are just at this moment too difficult to use because you need to know what the elevation of the land surface was to use land surface temperature proxies. And the continents move around, and there's mountains, and so it's almost impossible to use those for this kind of project to infer the past temperature changes. So, yeah, there's a lot of data, especially for the past 66 million years, but this is the temperature data. And then they used a climate model called HAD-CM3L, and they did climate simulations at 85 time slices for the past 485 million years. And so basically there's one climate simulation to represent every 5 million years or so. And for each of these time slices, they ran 8 different model simulations with different carbon dioxide levels and other model parameterizations, just to give sort of a range of estimates of the modeled climate. And these are the two data sets that go into the data assimilation. And basically, after the assimilation, compared to the original modeled climate, there's a lot more variation in the global average surface temperature, and that's because these proxy data is able to sort of correct for the uncertainties in the climate model. And so one of the things is that compared to the original model data, the assimilated data is on average 2 degrees warmer, so 24 degrees versus 22. So the average global surface temperature for the Phanerozoic is 24 degrees Celsius. But also that the variations in temperature went from 2 degrees to 5 degrees in the assimilated climate. So basically, the assimilated temperature reconstruction shows a lot more variability, which is probably a lot more realistic when you think about it. And it does fit with the assimilated reconstruction, does fit with the major ice ages that happened, especially in the Carboniferous, which was 300 to 350 million years ago, and the current ice age. And it also fits with the Cretaceous being a very hot period. And so the current temperatures are very much at the low end of the global compared to the global average temperature. The current temperatures are quite low compared to this 24 degrees average. So another thing that they found was that there's a strong latitudinal dependence on surface temperature, and this is much larger in these so-called cold house periods. So a cold house period is when global average temperature is below 18 degrees Celsius. And when you're in a hot house period, that's when the global average temperature is above 28 degrees Celsius. The variation in surface temperature between the equatorial regions and the poles is not so much. And so one of the statistics they found from the assimilation is that the Earth has spent roughly the same amount of time in cold house and hot house periods, and the cold house periods are when there's a lot of glaciation, and the hot house periods are when some parts of the Earth's surface were probably too warm to be hospitable to plants and animals. So you don't want to be in a hot house condition for very long. And another interesting result is that in the equatorial regions, there was a 20-degree difference between the cold house and the hot house periods. And this is a bit surprising because originally it was considered that the average temperature in the equatorial regions didn't really change that much between the cold house and the hot house periods. But this assimilated experiment seems to suggest that this is not the case. So that was very interesting. The final thing that they found is that, which was also a bit of a surprise, is that carbon dioxide provides the strongest control on global average temperature during the Phanerozoic. And the reason this is a bit surprising is that the sun is gradually the sunlight is getting more intense over time. So it was originally thought that the lowering of carbon dioxide that has happened in recent times was sort of balancing out the changes in this luminosity of the sun, and that seems to be not as strong as they expected. So there seems to be a fairly strong relationship between the carbon dioxide and the global mean surface temperature. This relationship is not so strong in the Mesozoic, so they weren't really sure why this was the case, but it's possible that because the Earth's surface temperatures were so hot that maybe there were other factors which were not taken into account in the climate models that was affecting the global surface temperatures. And the thing that they concluded is that the apparent climate sensitivity to doubling of carbon dioxide was 8 degrees Celsius, which is, if you follow climate change reports, they always talk about the climate sensitivity of doubling of CO2 is usually between 2 and 5 degrees, and this 8 degrees is much higher than that, and that's why they call it an apparent sensitivity, because this 2 to 5 degree increase in temperature due to a doubling of CO2 is for the current configuration of the Earth. So what they've done is of course taken into account the changes in the position of the continents, so that also impacts what your measurement of the climate sensitivity is. But the important thing is that based on their results, that once you start pushing carbon dioxide levels above 800 parts per million, you start to get into a warm house period. So with their results, even right now, the carbon dioxide levels still put us in the cold house state that we currently are in. But it is quite important to think that making sure that carbon dioxide doesn't go up so high will be important to ensure that the Earth doesn't face catastrophic climate changes. All right, that's the end of episode 3, and I hope you tune in next time. Thank you.